So welcome back. And in fact, this is the second time of my talk. I gave a talk last week, and then listened to the very nice, interesting talks. And I realized that I should give this talk that we didn't. This is a joint work with Hajime Kaneko and Donghwan Kim. And so this research seems to be quite related to this audience. And so my idea is that our idea is to somewhat understand the normality. And the normality, there are many discussions found like that. So as far as I understood, so this, you're given A and B, the fixed positive integer, integers greater than 1. And then, so A-adic expansions, A normal. So A normality means that, so this X is the number, so has A-adic expansions, which has a normality. So this any given pattern appears is so expected frequency in the A-adic expansions, and the B normality is of course different. In the B normality, and so if this A normality and B normality is sometimes equal. And it is already done, or quite well known, that so this A normality and the B normality and B normal. So this statement, if and only if that A and B are multiplicatively dependent. So this is a classical result. Then multiplicatively dependent means that there exist some m and n integers. So this is integer vector which is not 0, such that the A to the m is equal to the B to the n, like this. Okay. And many result is known that whenever, so if you have independenceness, then this set is different. So the set of A normal numbers and set of B normal numbers is different. And there are many results on the dimension result that the A normal numbers, which is not B normal, like that. And there's quite a lot of study of this. So we consider this kind of problem in a little bit more general setting. So, so we start with X, a space. Let's say this is a compact metric space. And then equipped with a Borel measure. So this is a set of Borel, this is a Borel set. And then so we consider this, so nu and nu. The probability measure, two probability measures. A Borel probability measure. And then we consider two dynamical systems. So this is so the quadruple of these. And the T, so this T is so mu is an invariant measure of T. And so X beta nu S. And we assume that both of them are ergodic. So this is the ergodic system. Okay. And then, so in such a regard, then so normality could be replaced. So this kind of normality is replaced, and we can say it in this way. So the normality means that we are discussing some generic point on this system. The generic point, the meaning of that, so this point, so x0 is generic, T generic. The definition is that so if you take the Birkhoff limit of some L1 functions and take the orbit of x0 and n0 to n minus 1 is equal to the space integral, so d of mu of x. This is the definitions of, and in fact, this holds for almost everywhere, so almost every point. And this is a Birkhoff theorem. So f for any L1 function. Okay. And so this is the definitions of T generic. And so if you restrict ourselves to the Lebesgue measure and T, so if T is something like a to A of x, yeah, countable families. But anyway, so in this case, so maybe this is nicer to look at this. So continuous functions, and this is because we are talking about the Bolero set. Yeah, in this case, this is not necessary, but to the rest of the talk, it's better to look at it in this way. And so if you restrict ourselves to the A-RE expansions like that, then so this x0 is T generic is equivalent to saying that x0 is A normal. If you take this invariant measure to be a Lebesgue measure, like that. Okay. Now, so the definitions comes in a natural way that the T and S is generic point equivalent. If the set of T generic point is exactly equal to the set of S generic point. Okay? Exactly equal. So we don't. So if you consider because if you look at the Birkhoff limit theorem, it is always true for almost all points. So this is not so interesting. Then it is always true. So because we are assuming ergodicity, so this is always true for if you assume that almost all points. So we are interested in every point. Otherwise, it's not so interesting. Okay, this is a kind of a definition which lies between ergodic theory and number theory. Number theory likes everything, and the ergodic theory statement is always like almost all. But this is different. Okay, this is a number theoretical statement.
So if you change from f in n1 to x in c of x, I think you get a set of T generic points which works for every f.
Yeah.
So you can
every f, yeah.
So instead of f in n1, you can take f in c of x. You have c of x is a set of x.
Yes.
So you get a set of generic points that you will only work for every f.
Yes, exactly. So in this sense, it's better to restrict ourselves to this continuous functions. Okay. Otherwise, so we lose some meaning. So if you talk about this equivalence, So the Birkhoff theorem should be described on the L1 space, but this definition should be done on continuous functions. Okay. Okay. Now, so there are some previous result regarding this kind of thing, and one is this kind of result. I think originally this is Schmidt, and there are many so extensions of such result exist, and then so maybe I memorized several results. So Schweiger and Van der Hey. So he somewhat corrected the former publications of Schweiger, saying that if T to the M is equal to the S of N. So this is in the sense of map. So T and S is somewhat multiplicatively dependent as a map. And assume that the T and S, we need some mild conditions. Then, T and S, T and S are equivalent. Oh, I wrote it this way. Yes. This is done. And you can easily imagine this kind of things, that if you come back to the A normal and B normal, if you look at the normal in base 2 and base 4, then it's just a change of the size of the blocks to 1 to 2. It's almost the same thing for normality. Okay. So this is this is kind of an extension of these results. But one question is whether the converse holds for this statement. And this is not the case. And the Nakada and Kreikamp gave two counterexamples that the converse statement does not hold. I write their result as a map. So they showed that this is a binary expansion. This is 1/2, and then another one is this is 1/2, and this is 1/4, and then like this. 3/4, correct. Okay, and then another one is like that. So if you take the golden mean, is one of the golden mean, and then it is like this. This is called the beta expansions, and then 1 omega, like that, and they are equivalent. Okay, in this way, and so clearly that these two maps is not in this sense multiplicatively equivalent, because the left side has too much. So if you make iterations, then close to 1 we have many iterations of the other. So the slope becomes higher here and slower here. So it cannot be. Okay. So but still this is equivalent. And their idea is to use the jump transforms. Is quite common in ergodic theory. That if you look at some small regions and look at the induced map, that the point comes back. We wait until the point comes back to these regions. And this is called we need to wait until the point comes back, and this is called the jump. And we consider this jump transformations preserves the normality in some sense. Okay. And the Bose trick is done by jump transform. Now today, I'll give our main result is like this, which is a kind of a generalization of those. So the main result so consider this. So setting is almost the same. So x is the 0, 1 interval, and we consider so T is so-called the beta expansions. So like this, which is beta x, like this, where beta is a Pisot number, which came, so last week we saw many times, but maybe I repeat. So this definition is that the beta is an algebraic integer and greater than 1, such that all the conjugates, so we consider other roots, which is a root of the minimal polynomial of the beta, has modulus less than 1 for j not 1. So non-trivial root, which is other than beta, has modulus less than 1. Like in this case, probably, so this beta, so this omega is satisfies this minimal polynomial, and omega is this number, but the conjugate is this number, which has modulus less than 1. And this is a golden mean. And in this case, this is Pisot number, because the other roots are less than 1 in modulus. And this is an algebraic integer, which means that this satisfies the integer polynomial with monic polynomial. Okay. So then there is a classical result that the invariant measure is described in a completely, so in this system, so this invariant measure called Pare measure, which is, so I write it in, so I didn't normalize in this way, that if T1 and n, T to the, so x, where this is 1 minus 0, and iterate. And then, so we have to normalize by some constant. And this, we consider this kind of functions that given x, then we sum up all the beta to the 1 over beta to the n, where the orbit of 1 exceeds x, then we sum up. And then so the measure is given in this way. So this hx dx. So this is absolutely continuous, the Lebesgue measure in this way. So this is so this gives the invariant measure of T. So the starting system is beta, and T and mu beta. Okay. So this is the first one. Maybe I changed the order. Okay. Okay. This is the first one. Is that okay? N is moving. N is moving. So we consider the orbit of 1, and then so if the nth orbit exceeds x, we sum n over n. So this is always finite. Okay. So this is the first one. And then the second one. We need the second one because we have to compare. And, and this, in the case of beta is an integer, this is the usual one. It's a usual, so A-adic or B-adic expansion is included in this sense. Okay? And then, so we subdivide, we prepare some subdivisions or partitions of I. So let's say I from 1 to L is a partition of 0, 1. That the AI is a proper interval. So it's not one point, but this is a proper interval. But we don't assume this is open or closed. But we just assume this is a partition. So it could be so some shape, closed or left open or something like that. All the possibilities allowed. But we only assume that this is partition. Okay? And S is a piecewise linear function of slope plus minus beta to some power. So each of the interval, so Si, S of x, has a shape plus minus, this is decided by the interval of mi x minus bi. Okay? Where x belongs to mi. Okay? And another assumption, this beta bi belongs to the field generated by this Pisot number. Okay, that's all the assumptions. So we consider this kind of setting that the slope is just plus or minus of the power of beta. And the intercept, we assume that this is, intercept is nice. Okay? And the assumption. Another assumption. So we assume that this system is ergodic, and there exists an absolutely continuous invariant measure. And we assume this is unique because of this ergodic. And then this measure, which I write, so this x, beta, and nu, s, with this is the invariant measure of S, and nu is equivalent. So equivalent to the Lebesgue measure. So this condition is a bit difficult to check. Usually. And we need to compute the density. And we need an explicit computation of the density. And this is a bit difficult part. Ergodicity is usually very easy to check. Okay. This just means that, I didn't say that this is also equivalent to the Lebesgue measure. So, which means that these two measures are comparable. Which means that there exists a positive, there exists C positive, such that for any Borel set, so we'll say Y, A, the C of, so C is greater than 1, C of, I wrote mu of A, mu A, C mu A, like this. Okay? So the two measures are comparable. In fact, this is not trivial, but so under this condition, this follows. And what we need is this equivalence, in this sense, of the measures. Okay. The theorem T and S are equivalent, are generic point equivalent. So everything is equivalent. So essentially what you need is the slope. Slope is Pisot. That's all, in some sense. And all the maps are equivalent. This is, I think it's, we are rather surprised that this is a very strong statement. Because before we use jump transformation in a very detailed way to prove this, but now we have a rather algebraic proof of this one, and the proof becomes very, very short. Okay. So I will tell you the consequence of this result. So look at this one. So this one, the beta is 2, and 2 is a Pisot number. So this is algebraic integer, and no conjugates at all. So this is okay, trivially true. It's a Pisot number. And so the slope is 2 here. And slope is 4. So this is okay. And then the intercept is belongs to the integer, so it's okay. And this one, the golden mean, so this beta in the golden mean case, so this is the t, and this one is, so this is beta, and if you compute this one, the slope is beta squared. Okay? So it's okay. Another example. So we consider beta to be an integer greater than 1, and then we divide these 1 over beta, 2 over beta, b minus 1 over beta, and then we put arbitrary slope, arbitrary order like this. So this is so we consider this Bureau expansions with changing slope, so positive to negative in this way. And this is equivalent to the beta adic expansion. So in this case, so Lebesgue measure is invariant. So this is so in a special case that so this binary expansions and the tent map is generic point equivalent. So the generic point is the same thing.
Your theorem also implies that S is also valid.
Yes, yes. Automatically. But we assume this one. Yeah, yeah. We assume this. Assume this to get this result.
So you
So all these are assumptions. All these are assumptions. Of course, if the generic point is equivalent, then this should be ergodic. This should be ergodic. So the converse. Yes, yes. But so.
You don't have to.
Is it okay? And then, so this is the first, so corollary. So that any kind of flips is okay. Yeah, I should assume this, yes, okay. And another consequence, So it's a slight generalization of this one, is that if you start with beta, Pisot number, without positive conjugate. So beta itself is positive, and we assume that other conjugate is not positive. Then, so by Handelman, showed that so under this condition is equivalent to the saying that so there exist some representations in this form, beta to the say mi and ai from 1 to say l, where ai is a positive integer, a non-negative integer. So under these conditions, the same thing. So we chop up these intervals. So this is a 0, 1 intervals, and we need the partitions of this I. We chop up in this way, so like this. And so each of them have a length of the shape b to the something, b to something mj, something like that. So all of them, because of this formula, one can sum up, one can divide 0, 1 interval in this way. Okay, and then put slopes in this way, in any order, like that. So this is a Pisot thing, like that. This satisfies our condition. So all of them are generic point equivalent. Whenever the Pisot number without the positive conjugate, one can have this kind of thing. And this expression, we have infinitely many, because so this expression, once found, then we can reproduce many different expressions of such. So which means that we have infinitely many different so expressions of this form, which means that we have infinitely many so different expansions, which is generic point equivalent, and the measure is Lebesgue. Now, final example. And final example is for me the most interesting. The final example is like this. So I rewrite. So the beta expansions, beta greater than 2, and we write this kind of expansion. So this is beta expansion. So this t of x is beta x, where beta is a Pisot number. Then we get this kind of shape. This is the first map. As I mentioned, that this beta and mu beta t. And the second one is like that. So I write it in the case that beta is less than 3. So it's until some point it is the same. So this is 1 over beta, and it goes in this way. Mu beta is defined by so invariant measure of this one, which is unique. And I wrote an explicit shape later, before. Okay. So this is an invariant measure of that. And this one, So we chop up at some point, which is a bit smaller than 2b, so it is like that. And eta is some positive number. No. You are, because remember that our assumption is only on the intercept. We don't care about the, these divisions. Oh, you remember? So this one is general. Okay? These sections, so these partitions is general, but we only assume that this intercepts belongs to the Q of beta. Okay, this satisfies these conditions, okay?
So you have
uncountable numbers of that. Uncountable. And this is usually non-Markov. So non-Markov system. And then, so x beta, and so this some invariant measure, I write it as S. Then, so one can prove, one can get the explicit formula of this mu of S, which tells us that this is also satisfies these conditions, that both two measures are equivalent to the Lebesgue measure. Then, so this gives uncountable family of maps that are generic point equivalent. It's a very strange example, okay? Because this is no Markov. All the maps before were Markov. So this is a very strange example of a generic point equivalence. Okay. Now, then I'll tell you something about the proof. How, and so it's the most important part of the proof. So in fact, the proof, we have two ingredients. So essentially, we have two ingredients. So one is, so I cannot write it in a criterion. So it's called the Piatetsky-Shapiro criterion, but maybe I misspelled his name, but I'm sorry for that. So it's the old result of that for the generic point. So it is like that. So given ergodic system, like so this mu and S, it's ergodic. Then, as I said, that the definition is that for any Borel set, so Borel set, so we consider the Birkhoff sum of this C characteristic. So this is so C of x0. Oops. Sn of x0 n from 0 to n. This is a Birkhoff sum. Okay? And if you take limit of when n makes large, and if x0 is generic, then it so converges to the integral over the space. But the Piatetsky-Shapiro gave a weakening, so relaxing of these conditions in this way. So there exist, this notation is not so nice. So maybe CM, okay? And then, so limit soup is bounded by M of a measure M, C. And even so, one can restrict ourselves to some generic set like semi-algebra generating this Borel set, and then which implies x0 is S generic. Yeah. Mu is a ergodic measure. So it's a system. So this is the invariant measure. First of all, it must be an invariant measure, so which is something like a T inverse of A equal to T. This is called invariant. And also, the system is somewhat unique, so cannot be divided into two. Yes, yes. So this applies to rather general system. And the only point is that we want to find a uniform constant that the limit soup is bounded by the expected value. This is a Borel set. This is a Borel set. Maybe. Sorry, you're right. Sorry, maybe that. Yes. So C is a semi-algebra. Generate. Sorry. It cannot be. Yeah, you're right. So we have to look at the semi-algebra, and we want to have this kind of situation. And so, yes, you're right. So this criteria is known as sometimes the hotspot theorem or something like that. Sometimes it calls hotspot theorem. Because so if you assume the contrary, that it is not generic, then there exists arbitrary large n that this converse holds. So we have a hotspot that the points get together at some very near to this point. Okay, so this is called hotspot. Okay, this is the first theorem, and the second is Pisot things, and why the Pisot things comes in. So maybe I don't want to speak too long. So why the Pisot comes in? This is the main point. So Pisot, and consider some set like this. So it's say Ci beta to the I from 0 to some L, and Ci belongs to some set which is a finite set belongs to Q of beta. And then, so this, sorry, I have to write it in a proper way. So we consider this is a finite set in Q of beta, and the Ci belongs to F, and L is an integer, like this. We consider this kind of set. This is a set of a form generated by polynomial, and the quotients in Q of beta. Okay. Then I claim that this point set is very special, very special. It is called uniformly discrete. So this is a main ingredient, and so this uniformly discrete. I repeat the definitions I explained to you last year. I don't know, last week. So this is that there exists some R positive, such that the gap of 2 points, so is larger than R. Any point is separated by some constant R. Then we say this is uniformly discrete. And this is a very rare phenomenon that we cannot expect. So the Pisot, whenever this is the only case, probably only case, the beta is Pisot. Okay? Ah, sorry. Okay. Yes, they exist in R. Okay. Only case. That this point set becomes uniformly discrete. Okay, and this is a rather easy to prove, and just making some taking a norm of this number, and then which has some lower bound, which come from algebraic considerations. Then we get this kind of lower bound. It's a rather well-known method. And then how to combine these two? So the main okay. So the idea sketch. So t of x should be written in this way. So some di, and the d is an integer. So this is an integer. Okay, and the s of x is written in this way. So plus or minus. So I write it in plus. This is plus minus, and beta to the m I depends on x, and say something d I like that. Okay, and the di belongs to q of beta. Okay. So essentially, we have to compare this orbit of t and orbit of s. Okay. And if you compare, so if you iterate, say for example s to the n of x, then if you apply many times, then the leading term is like this, with sum of something like I something, and this I is very sensitive to the points. So this is some number. It's a polynomial of x and some polynomial. So I write it in a very vague way. So b to the sum of something to the some di. So we have so if you iterate, then what you get is something like that. So this is a b to the power plus minus b to the power, and then the digits come from di. Okay. So this part is a bit difficult to write down. Okay. The same thing for this. Same thing for this one. But this one, the di is an integer. Okay. So we prepare for this set of f all the so plus minus 1, so 0, plus minus 1, plus minus 2 to plus minus beta for the safety, and plus minus d1. So this is maybe too much. dm. So I wrote it L, I'm afraid. Like this. We prepare many digits. We consider this kind of thing. Then, and apply this criterion, the uniform discreteness. Then all the points have a minimum gap between them. So if you consider all the polynomials. So we look at these, these part, and say, so we have to coordinate in a different way. So this x, this is some beta to the x, and some polynomial. So beta j di, something like that. I don't know. So we have to compare these two parts. But we have to be careful about this part. We need to make this almost the same order. So we wait until it is almost the same slope. And then compare the difference between them. So we consider the semi-algebra depending on this. In this case, this is semi-algebra is a semi-open interval. And then so we have only finitely many shifts of this semi-interval, which describes this sum. And then so apply this criteria of Piatetsky-Shapiro criterion, gives you the desired result. So this is a very, very simple proof. So this is, the proof is 2 pages or 3 pages. So it's a very easy proof. So I think it's all over. Thank you very much.
System you're describing is the old job where is this is this dynamical system with specification errors?
Yes, the dynamical system with specifications. Yes.
The reason I'm asking is it's really good what we talked about after my talk, where you mentioned the cases we have binary normal numbers with the same as generic functions like that, and it gives another proof of this.
Yeah.
I'm just wondering if there's any sort of way you can get new results proven on the proof that I think.
I'm hoping so.
So basically, kind of the question is there some way that you can do something like what you did there to get us some dynamical system without really any real level specification? And if so, then you can use our main theorem to show that the generic ones are higher.
Probably. I think that you are aiming at some descriptions that the set is in a same or different Borel hierarchy in this sense. But so maybe that this kind of method.
Our theorem is something working when we have this there's some sort of version specification. If we don't have that, then there really isn't anything to do
without specification. Maybe that. So this contains quite a lot. So sometimes it doesn't. So there are countable points that we have. It is sophic, and this is non-specification case exists. So many more. So generic choice of eta. This satisfies the specification property.
There are some.
Sorry.
There are some choices of data where you don't set that.
Yeah. So if you take so eta to be in Q of beta. So then this becomes sophic. So in this case, that this does not satisfy specification property. Sometimes.
What we had wasn't exactly specification. It was slightly weaker version. I can show you that. But then, maybe there's a chance to have some.
Yeah. So wait a minute. So specification means that we have wrong rung of zeros, I think. No? Wait a minute. I made a mistake. Sorry, I made a mistake. So suffix. Sorry. So this satisfies specification. Sorry. The other way. So we find some point which is non-specification exists. Yes. Sorry. Yes, so there are some descriptions done, some paper by Blanchard describing some set of beta, that the beta expansion gives you a non-specification case.
So here, considering those set of points that are T-generic or S-generic, looking at one generic, does anything happen if instead of looking for equality, I look for a subset?
Okay. This is in fact, as far as we found with Donhan and so Hajime, that there are some results describing some case where the T generic point is included in S generic point. There are such results in countable partitions of this. So in this case, we only consider some piecewise map, which is so this partition is finite. But if you consider countable dissections, then we have such an example that so this S generic point is included in T generic, but not the other way around.
Are there any relationships between the different zero numbers? So, for example, if we look at these nice classes, the zero number here is a collection of points that are generic or that number in this class. If you change the zero number, is there any relationship between those?
This was interesting questions, but so we don't know anything. That if it is beyond multiplicatively dependent, then we don't independent. We don't know anything on the Pisot case. So in the integer case, it is if and only if statement. That generic point equivalence is equivalent to multiplicatively dependentness. Pisot case also. Really? But this is for beta expansion case, I think, no?
No.
Every beta slope.
It's not beta expansion, so it's the sequence distribution.
This is a question for Yang.
Same regular questions. If you take another measure as the pi measure, and both maps are equivalent to this common measure, you don't go through the big measure, would it still work?
So in fact, generic point equivalence, the concept is on the set, not on the measures. So measure is not relevant. Okay. So, this means that the point sets, all of them are equivalent.
Consider the genericity with respect to the convergence to this measure and points that satisfy.
This is a different question. So, yeah.
Are there more questions? So, thank you.